Okay, welcome to Let's Get to the Marks, going through the GCSE Combined Science Trilogy, Paper 2 Chemistry. You got an hour and 15 minutes. There are 6 questions. What I recommend is you pause the video at the start of each question, have a go on some scrap paper, bust out your calculator, get a pen, and then unpause and watch the explanation. Okay, let's go through this first question. A student investigated the colors in a brown ink using chromatography. 1.1. Figure 1 shows the apparatus used. Figure 1. We have a chromatography tank. We have chromatography paper put inside the tank. We have a solvent. We have a starting line along here, and it says the starting line is drawn in ink. We then have a red color, blue color, green color, yellow color, and a brown ink. Give 2 errors made by the student. Describe the problem the error would cause. Let's get some space for that. Okay, so can you spot the errors? Why don't you pause the video, study the diagram, and then unpause and I'll go through the explanation. All right, I'm going to go through the errors. So there's a couple of errors. First of all, look at the solvent. The solvent line is starting above all the ink. So what would happen there is these inks would dissolve and disperse into the solvent and they would spread and run and they wouldn't climb up the paper as we actually want. So we need to put that into words. So error 1, the solvent starts above the inks. This means, well, so error 1, the solvent starts above the inks, and then it wants us to write the problem down here. So this means the inks will dissolve or spread into the solvent. So they'll spread out and it will be kind of ruined and we won't get any chromatography. And that's the first 2 marks. Let's look at the second issue. Okay. So I need to scroll down to do the second issue. Can't fit this in. Okay, there we go. Lovely jubbly. In fact, I think I can bring back my original answer for number 1. Let's move that up there. There we go. Bish bash bosh. So let's go to black. Right, the second problem is you see the start line here. Again, this is drawn in ink. The problem with having that in ink is it means the start line itself will dissolve and spread up the paper and blur in with all the different columns of color that you'd expect in chromatography. So you just get a big mess. Okay, and we don't want the ink itself dissolving. So it's best to do it in pencil. Pencil? In pencil. All right, so error number 2, start line in ink. Ink might dissolve and dissolve in the solvent and spread, ruining the results. It should be done in pencil. So we normally use pencil because pencil is not soluble in most of the solvents used in chromatography. So there we go. Okay, let's move on to the next part of the question. So that was a nice 4-mark starter. A different setup, sorry about that, a different student set up the apparatus correctly. So you can see it's correct now. Figure 2 shows the results. Give the 2 conclusions the student can make from figure 2 about the 4 colors in the brown ink. So we've got brown ink here and we can tell, look, it's split into 4 pieces. So there are 4 colors in the brown ink. They've asked us for this, which is really important, which is 2 conclusions. Now, what is a conclusion? A conclusion is a fact, something that you can, so facts, people, we need to come out with the facts. This is something which you have the receipts or the evidence for, all right? So basically, you need to be able to bust out the evidence to back these up. And don't be trying to say stuff that you're just guessing at. A conclusion is just pure fact from the data. You don't need to explain or use any of your science. So facts from the data. Right, we know that there are 4 colors, but what can we say about the 4 colors? We can say that one of these 4 colors, look, it matches with red. So one of the four colors is red. Another one of the four colors is yellow. So we could say two of the colors, one color is red, one color is yellow, and look, one color is blue. And then we could also say one of the colors is not red, blue, green, or yellow. This color here that's in the brown ink doesn't match with any of these. So what they've done is they've run a mixture, which is the brown ink, against pure yellow, pure green, pure blue, and pure red to see which of the colors in the brown matches. So what we can say here is, look, there's no, it looks like there's no green in there. So there's loads of conclusions. I'm going to give you the different ones. So we could say the brown ink does not contain green color. So we can tell that because if you look at the green color, it doesn't match with any of the four colors in the brown ink. So that is a pure fact. Another fact, I'm going to give you all the facts here, folks. Another fact is we can say the brown ink contains, and these could be separate marks depending on the mark scheme, but it contains red, yellow, and blue. Red, yellow, and blue colors. Now, maybe that's 3 different points and they could get you the 2 marks, but you never know with the mark schemes. So there's definitely 2 separate points, possibly 4 if that's 3 separate points. Something else we can say is that the brown ink contains an unknown color which does not match red, blue, green, or yellow. So we can say the brown ink contains a color that is not yellow, what do we say? Blue, red, or green. And there we go. So an unknown color. And so any of those is going to get you those 2 marks, and they're conclusions we can make about the brown ink. Something else you could be asked, and we might be asked later in this question, is why did the green ink stay on the line? And you might be able to think what the answer is to that. And another question that would be typical, so you haven't even scrolled down to see what the questions are. Another question that would be typical in chromatography is sort of explain which color was the most soluble in the solvent and which of these colors do you think dissolved the best in the solvent. And you should be able to answer that, and you should be able to answer why the green color stayed on the line. Okay, let's go down and see what the questions are. Oh, check it out. Why was the green color still on the start line at the end of the experiment? So that's a very typical sort of question. That's why I guess that one would be there. And the experiment was left too long. The green color was insoluble. The green spot contained too many colors. The green was too small. It's actually that it was insoluble in the solvent, so it didn't dissolve. Therefore, if it didn't dissolve in the solvent, it couldn't climb up the filter paper. Okay, it didn't spend, or if you want to use technical language, it didn't spend any time in the mobile phase. It spent all of its time in the stationary phase. So that's why it was insoluble. Now, they didn't ask us which was the most soluble. And if we went back up and looked at the diagram, you might have guessed when I asked that question, the most soluble was blue. And that was because it traveled the furthest in the same amount of time. So the blue color had traveled the furthest. Now let's look at 1.4. A student calculated the RF value of the color to be 0.24. The color moved 1.8 from the start line. Calculate the distance the solvent moved. Now, they've been really nice and given us the equation. They don't always do that, but essentially RF, which is the retention factor, is equal to the distance moved by the color divided by the distance moved by the solvent. Now, we've been told that the color moved 1.8 from the start line. Calculate the distance the solvent moved. So it's 1.8 divided by distance moved by the solvent. Let's call that D. And the RF we've been told is 0.24. So let's rub that out and put 0.24. Now, I don't know if you're any good at rearranging equations, but I like to put triangles. And if you know what's on the top of the dividing line, and we know it's 1.8, that goes at the top of your magic triangle. And then at the bottom goes 0.24, and then my unknown times D. So if I want to work out D, I'm going to do 1.8. This is a divide line divided by 0.24. So 1.8 divided by 0.24, and that's going to give me D. So I'm going to put that here, 1.8 divided by 0.24, and that is going to equal D. So Where's my calculator? So we want to do 1.8 divided by 0.24, and that equals 7.5. And then we ask ourselves, does that make sense? And the solvent would always move further but than the things that are dissolved within it. If you think about it, the solvent is moving up the paper, it's carrying with it the different colors. The colors cannot move further than the solvent, so the solvent must always move further. And so 7.5 to 1.8, that makes sense. Okay, cool. And that's going to get you three lovely marks. Awesome. All right, let's move on. And that's the first question done. Right, we're on to 2.1. Water that is safe to drink is called potable water or potable, however you want to say that. Compare how easily potable water can be obtained from wastewater, sewage, or groundwater, fresh water. So it's asking us to compare. So really, you kind of like the way I would break this question down is I want to explain how wastewater is treated for 3 marks, and then how we make potable water from groundwater, which is the normal method, 3 marks. So really, if you can get most of the processes that go on with treatment of sewage, and if you can get most of the processes that go on with the treatment of groundwater, we're going to get all the marks, right? Now, you could compare, as in, say, things that are similar between the two and things that are different. So when you see compare, things that are similar and things that are different. I want to compare these. So really, let's look at wastewater. So wastewater, what's the first thing they do with wastewater? So this is water from toilet, from sewers. So this is the stuff that goes down the shower. This is the stuff that goes down the toilet when you flush the toilet. So yuck. How do we prepare this so that people can drink it again? Well, only some of it goes back into that, and some of it goes into farmlands and things like that, where people aren't going to drink it directly, and some of it goes into cleaning in factories and industry and stuff. So wastewater from the toilet, from the sewers, what happens to it? Well, first it is screened. Now, to remove twigs and large debris. So this is going to remove large lumps and bits that are inside the sewage. What's the comparison with water? Groundwater is when it's rained and you've got water like sitting on the earth. We call that groundwater. And well, we've got groundwater underground, like in aqueducts and things like that. Anywho, what do we do with that rainwater basically? Well, we also have to screen it, but we don't call it screening, we call it filtration. So what we want to say is, because we're doing a comparison, I want to use terms like whereas. So whereas groundwater is filtered with sand and pebbles. You kind of make like a sand and pebble filter to remove, um, again, to remove debris and stuff like that, to remove large particles and large particles. So you're kind of removing large bits and pieces. And you're doing that like that. Now, next, what happens with the wastewater? Well, the wastewater is separated by wastewater is, I can never spell separated. I never know how many A's or E's are in that word. Wastewater is separated into liquid waste called effluent and solid waste called sludge. Nice, eh? So basically, the solid feces, all the poo and stuff, goes to the bottom, and the liquid just floats to the top. And we call this, is this sedimentation? Yeah. So wastewater is separated into liquid waste called effluent and solid waste called sludge in a process called sedimentation. So they just let the solid fall to the bottom. Effluent has two F's, doesn't it? Yeah. They just let the solid waste fall to the bottom and they separate it out. So essentially, you have like your solid waste from the sewage, all your poo and stuff down there, and then you have the liquid waste there. Okay, so liquid and solid. Now, what happens is the liquid waste is digested aerobically. And that means they use bacteria to break it down aerobically. And the solid waste is digested anaerobically. And that generally goes to be used to turn into fertilizer. So solid waste digested. Oh my days, digested, whatever that means, digested anaerobically, um, and used for fertilizer. So again, that's by bacteria, by microbes. I probably should make that, I should say aerobically by bacteria. Let's just put by bacteria because, that all could be a key point. So, and this is by bacteria as well, kind of running out of room. And then uh, finally, both the groundwater and wastewater are treated with ozone, chlorine, or UV, which is ultraviolet light, to sterilize and kill microbes, basically to kill pathogens, disease-causing organisms. So both of them will be treated like that. So what we can look at here is that the groundwater just had filtration followed by that. Whereas, so these were the ones for the groundwater. I'm going to put it there. We've got G and G. Whereas if it was the wastewater had this bit here and this bit here and this bit here. So there are more steps in the wastewater. So we want to actually say as a bit of a conclusion, which I've run out of room, so I'm going to put over here, wastewater treatment involves more steps. So is more complicated. And I would imagine it's more expensive as well. So that would be my comparison, really. And I should get all the lovely jubbly 6 marks for that. Let's move on. 2.2, which process can be used to produce potable water from salty water? So you've got some countries where it doesn't rain at all, right? So places like United Arab Emirates, some different places, we don't get a lot of rain. How are they going to get their drinking water if there's not so much groundwater because it doesn't rain? So they could use electrolysis, distillation, filtration, sterilization. Which one sounds right? Well, actually, what they're going to do is distillation. They're going to evaporate the seawater and hopefully condense it. And yeah, if they just evaporate the seawater and let it go off into the air, then they won't get any potable water. So they will have to do distillation where you evaporate the water and then condense the water back and you get fresh water that way. Obviously, a little bit more expensive. So water is more expensive in those places because you need the heat. The salty water contains sodium chloride. The scientists collected 2.40 grams of sodium chloride from 150 centimeter cubed of salty water. Calculate the concentration of sodium chloride in grams per decimeter. And now there's an equation. This has come up every single year in GCSE, normally in paper 1, sometimes like this in paper 2. And you need to know this one off by heart, and it is mass over concentration times volume. So have a look. We need to calculate the concentration of sodium chloride in decimeters. So what we need to do is mass divided by the volume equals the conc. One little trick, this must be converted into dm. As you can see, dm, and we've been given centimeters. So how do we do that? Well, first step, let's convert that volume into dm. You're going to divide by 1,000. 150 divided by 1,000 equals 0.150. I'm just going to leave it as 0.15 decimeters. So that's when you convert centimeter cubed to dm, you need to divide by 1,000. Now we have this. This is the volume. I mean, I suggest when reading through, identifying what you've got and writing them down. So once you see you have mass and volume, you'll know you need to use this equation. You need to know off by heart, m over cv. And then all I need to do is put the mass in. So we're going to go 2.40. That's the M. We're going to divide that by 0.15. That's the V. And that is going to give us the C, the conc. Let's whip that in the calculator. 2.4 divided by 0.15. And that equals 16, folks. So 16 what you're saying? Well, that's grams per decimeter. 16 grams per decimeter. Let's smash in the marks, right? One for the conversion of the volume, one for rearranging correctly, doing M over V, and one for busting out the correct answer. Three lovely jubbly marks. Let's move on. Okay, question three. So this question is about the reaction between sodium thiosulfate solution and hydrochloric acid. The equation for the reaction is sodium thiosulfate aqueous plus 2 hydrochloric acid goes to 2 sodium chloride plus water plus sulfur dioxide plus sulfur. Oh my days. I mean, yeah, we'll come to that. Normally, when I see equations like this, and you might not need to use it in this question, I would write the ratios down. So I'd be like, right, sodium, that is one, that is two, that is two, that is one, that's one, that's one. Now, the reason why I'd write these ratio numbers down, and you get that from the big number in front of the compounds, is because later on they might ask us to do moles. And when you're going to use moles, you often or nearly always need to use the ratios in the equation. It's why we teach you to balance equations. So the mass of the conical flask and contents was greater at the start of the reaction than at the end. So what they're telling us here is that they had a conical flask, and inside the conical flask at the start was HCl, and that is AQ, and Na2S2O3. Oh my gosh, that is some crusty level 2 GCSE art drawing. Right, so that was at the start. Then they're saying, check out. So these are known as the reactants, and these are the products. Now check the products, check the state symbols. What do you spot? I don't want to redraw all that out, but I will do that for you now. Okay, so you can see at the start we had hydrochloric acid and we had this sodium thiosulfate solution. And at the end, you've got sodium chloride, the salt, you've got water, which is a liquid. The salt is dissolved in water, so it's aqueous. And you have solid sulfur. But you also had some sulfur dioxide. But of course, G, that's a gas. What's happened to it? It's escaped. So whenever you see they're checking on your knowledge of state symbols here, and they're getting you to apply your knowledge. So as that's a gas, it's escaped. Of course, if they put a bung in, it wouldn't have. So we go sulfur dioxide is a gas and it escaped from the conical flask. Now, I'm not sure exactly what's on the mass scheme, so I'm also going to say sulfur dioxide has mass. I know it sounds stupid, but you might think a gas doesn't weigh anything. But of course, it's made of atoms. It has mass. It's escaped. So it can't be as heavy as the reactants were at the start. So we've lost the sulfur dioxide gas. Cool. I think you really get the marks for saying you're losing sulfur dioxide because it's a gas, and that would be both marks. Right, let's check out what's going on here. A teacher demonstrated the reaction between sodium thiosulfate solution and hydrochloric acid. Figure 3 shows the experiment. Here's figure 3. We can see we've got conical flask. We've got sodium thiosulfate solution and hydrochloric acid in there. We've got a black cross underneath the flask on a piece of paper, and they've got a timer. Figure 3 shows the experiment. The experiment was done in a fume cupboard, so it sounds like it was dangerous. They don't want you breathing in something. This is the method the teacher used. Pour 50 centimeter cubed of sodium thiosulfate solution into the conical flask. Put the conical flask on a black cross drawn on a piece of paper. Now pour in 10 centimeter cubed of hydrochloric acid into the conical flask and beep, start the timer. Stop the timer when the cross can no longer be seen. Repeat the experiment at different temperatures. So you can probably in your head be thinking, what type of improvements can you make? They might ask that. And they've said, what type of variable is time in this reaction? So is time the control variable? You're recording the time. Is it the independent variable or is it the dependent variable? And the way I work this out, independent variable is what you change. Normally it's at the end of the method. Repeat the experiment at different temperatures. So that's the independent variable. The control variable is what you keep the same. Obviously, you can't keep the time the same. You're not doing it for a set time. And then the dependent variable is what you record, and that's what they're recording, the time taken. Okay, so it's going to be the dependent variable. And it's hard to really teach you a way to remember that, other than that The dependent variable depends on the experiment. So the time it takes for the crust to disappear isn't down to the human who's doing the experiment. The time taken for the crust to disappear is dependent on the chemicals reacting in the experiment. You don't have control of that. Whereas a control variable is what you keep the same, like the concentration of the acid or the volume of the acid. And the independent variable is what you change. So it's independent of the experiment. The experiment doesn't change the temperatures. The human is repeating at different temperatures. So that is the independent variable. Anyway, it's very hard to find a way to remember that. You just got to do it. All right, 3.3 shows the results, temperature and time. What I would say as well, a good thing to memorize if you haven't memorized it yet, put it on a revision card. In a results table, the independent variable is always in the first column and the dependent variable is always in the last column. So we could have worked out the question before by knowing that off by heart. IV followed by DV in the table. Okay. Complete figure 4. So you should plot the data from table 1 on figure 4. Draw a line of best fit. So what I need to do very quickly is write these down so I actually know what I need to plot. 1 secondo. You can just see how I'm doing it. If you're someone who loses marks on the graph, then you need to pay attention to this bit. So sometimes they'll ask you to label the axes. And once again, the dependent variable always goes on your y-axis, and what you change goes on the bottom, which is the independent variable. And you'll find that in the first column of the table. So what we have to do here is when the temperature is 19, each one of these squares is worth 2. So when the temperature is 19, bang in the middle of this final square before 20, the time in seconds was 82. So I need to come up here and do that dot there. Why am I doing it there? Each one of these squares is worth 2 because there's 5 squares with a value of 10. So the next point is 32 and 48. So I want to go to 32, which is there, and up to 48, which is there. And then I need to do 45, which is going to be bang in the middle here, and 43. So 43 is going to be there. And then 52 and 15. So that's 50. 52 will be, each cube is worth 2, and then 15. So bang in the middle of 20 and 10 on the seconds. And then I have 63 and 7. So 63 is back in the middle there, and 7, that is 6. So 7 is there. Oh, it's looking a bit odd, this, isn't it? 73 and 3. 73, so this is 72. 73 is right in the middle there, and 3. So 3 is there. So actually, we can now put a curve of best fit. And how to know whether you're doing a line or a curve of best fit? Well, check this out. You can see, does it look like a straight line? No, it looks like there's a gentle curve. So you just have to kind of know. And I'm skipping that because to form, oh, nearly didn't go through them all. And there's my gentle curve. And if I wanted to continue on, I could continue on. Sometimes you want to continue the graph on and you're just going to predict where your curve's going to go in a smooth line. That was terrible. All right, I'll get rid of that. But they could potentially, and I can get rid of that bit at the bottom, they could potentially ask you to continue the graph on and make a prediction about something later on, and that's what you would do. Okay, they're probably going to ask me to circle that. Do you know what that's called? That is an odd result, otherwise known as an anomalous result. Anywho, plot the data, draw a line of best fit. It's worth 3 marks. So you'll lose a mark if one of these is really far out, but you're allowed to be half a square out for any of those plots. All right, let's go. Oh, a student investigated the effect of concentration of sodium thiosulfate on the time taken for the reaction at room temperature. Figure 5 shows the results with a tangent drawn at 0.4 mole per decimeter. So we've got a tangent here at 0.4. Calculate the gradient of the slope of the tangent at 0.4 mole per decimeter and give the unit and its 4 marks. How is that 4 marks? Right, let's zing in a bit closer. So we need to work out the gradient. So you can pick anywhere along this, draw a little triangle, and then you just want to divide. To find out the gradient, you want the change, and this triangle can mean change in y over the change in x. Now, we can draw a triangle anywhere along here in order to calculate the gradient. And look, I'm going to do this the easiest way I can, and that is I'm just going to make a triangle. So I'm going to draw that is some crusty triangle like that and like that. And then I'm just going to do the change in y over x, right? So if we look, it's easier to look at x first of all, because it goes from zero point 0.1 to zero point 0.6. So I'm going to do zero point 0.6 minus zero point 0.1 equals change in x. So that equals zero point 0.5, right? That's my change in x, 0.5. Now I need to do this. This is a little bit more difficult because that is 4. Each one of these is worth 2. How do I know that? The value is 10 divided by 5. Each square is worth 2. So that is 4. And then that is 14, 15. So I want 50. Oh, whoops. So 15 minus 4 equals my change in y. And that's going to be 9. So I'm going to do 9 divided by zero point 0.5. So let's go 9 divided by zero point 0.5. That equals 18. So it's going to be 18. And now what is the unit? It wants me to calculate the gradient of the slope. And you just need to do this and this. What did I divide by what? So y over x. What are the units for y? That is seconds. And what is the units for x? Mole per decimeter. So I want to go seconds per mole per decimeter. So per mole per decimeter. Now there are a lot better ways to write that. So okay, let's give ourselves 4 marks. I'm not really sure what the 4 marks are for. I think they're for working out the gradient. So for working out the 9, for working out the zero point 0.5. Now, your numbers could be different because you could have picked any 2 points along here. You could have picked any 2 points to do this. I just happened to do that. And then that for the answer, and then 1 for the units. Okay, let's move on. The student determined the rate of reaction at regular time intervals during an experiment. Explain why the rate increased during the reaction. You should give your answer in terms of particles. Sorry, I totally read that wrong. Explain why the rate decreased during the reaction. Okay, so during every reaction, the rate, the speed at which the particles collide with each other will decrease. And the answer is, like, imagine these are my reactants. So I've got pink balls, right? No diddy. And we've got blue balls. And they are reacting, okay? They are colliding with each other, okay? They are colliding with each other. Bang! Well, the more they collide, okay, so woo, the more they bang into each other, this is not going well, is it? Right. The more they smack into each other, what's happening to the reactants? And imagine they smash into each other and they make something new. There's less of these to bang into each other. So the probability that a blue circle and pink circle are going to smash into each other is decreasing as the reaction goes on because there are less reactant particles, so there are less collisions. So as the reaction oh gosh, goes on, as time goes by, there are less reactant, can't spell, reactant particles. So there are less frequent collisions. So a lower rate of reaction. Basically, the reactants are getting used up. What I should have said is I want to also tell the examiner that I know the reactants are getting used up to make product. So I'm just telling the examiner that I'm aware that the reactants come together and they make products, and therefore there are less reactants, so less chance of a collision. And that is kind of what I wanted to say. And I wrote it in pink, which is highly annoying because it's harder to see, obviously. All right, let's go on. It's all about time, though, isn't it? Saving time. Right, let's go. 4, the question is about hydrocarbons and the uses of hydrocarbons. 4.1, figure 6 shows a model of an alkane. So this is an alkane. Name the alkane in figure 6. So what you need to do here, you need to recognize what alkanes are. So alkanes are made of, what do we call alkanes? Alkanes are you know the answer. Alkanes are hydrocarbons. Okay, don't know why it went caps, but alkanes are hydrocarbons. So they're made of carbon and hydrogen. You can probably guess. If not, I'm going to show you anyway. You might want to pause the video, see if you can name it. Right, these are carbons and these are hydrogens. That might give you a clue. So you can work out the formula is four C's and how many hydrogens? One, two, three, four, five, six, seven, eight, nine, 10. So H10. So do you know the name of a alkane with four carbons? It is butane. And there we go. One mark. Wunderbar. What is a hydrocarbon? Well, look, hydrocarbon, what's it made of? So it's one mark. You can probably just say something made of carbon and hydrogen. Personally, they used to give these as two markers. So I'm going to write the two mark version, and it is a compound, and it has to be a compound because it's made of more than one element, made of hydrogen and carbon atoms only. And they used to be really specific about that. It used to be a two marker. You had to say carbon and hydrogen only to get the two marks. Nowadays, they might just say you just need to say it's made of carbon and hydrogen, and you don't have to say only. Okay, cool. Right, let me move on. Blops. Large hydrocarbon molecules are cracked. 4.3, when C11H24 is cracked, three products are formed, complete the equation. So there's a little bit of sort of mental math here. All of your numbers here, 11 and 24, need to equal 11 and 24 here. And any way that you can do that, you're going to be good. So it makes C5H10. So I kind of want to go C11H24, and I kind of want to minus C5H10. And that is going to give me, I've got C6, H14 to play with, but I've got to split it into three things. How annoying is that? Right, so I'm going to go, it's going to make C2. You always make alkenes as well, but they've made an alkene there. What if I go C2H6? That ain't going to work. I'm going to go C2H4. So if I do C2H4, gosh, this one's quite hard. That's going to make eight of those, and that is going to use four of those. Okay, so if I take away, you've got to remember this is a coefficient, so that's like a multiple. So if I then take away C4H8 from C6H14, I'm going to be left with C2H6. That looks a bit confusing on the old screen, but that's an H. So if I have C6H14 left after taking away this first bit, then I end up with C6H14, and then I minus C4H8 because I put a 2 and a 4 there, and that leaves me with C2H6. That was quite difficult for those ones. Yeah, sometimes they're a lot easier than that, but there we go. Right, explain why one of the products of cracking is in high demand. So you can pick either one really. You've got this is ethane, and that is small alkanes are really good as fuels. So small alkanes are useful as fuels. So they're really useful as fuel. Small alkanes burn easily. They're in things like the Bunsen burners you use at school. They contain a mixture of small alkanes. And then you've got here alkenes. How do we know this is an alkene? Because it's not CnHn H2n plus 2. It's basically it's you only have double the hydrogen of the carbon, then you know you're dealing with an alkene. So this is an alkene, this is an alkene. If it was an alkane, it would be CnH2n plus 2, so it'd be C5H12, and this would be C2H6 like that. That'd be ethane. This is actually ethene, okay? This is an alkene called ethene, and this is an alkene called pentene. Now, do you need to know that off by heart? No, but you should be able to spot their alkenes. And why are alkenes good? Well, alkenes can be made into plastics or polymers, which are plastics. So I'm going to say, I'm going to explain one. So I'm going to say alkenes um, can be made into polymers. And just in case The examiners are getting arty-farty. I'm going to put plastics. Okay. Now I could have said small alkanes like ethane are useful as fuels because they burn easily, but I decided not to. It asked for only one, so I'm just giving them one. There we go. Bosh. Right, 4.5. Window frames can be manufactured. Oh, our sensor 6 mark. Analyze the table. I might as well shoot myself. Window frames can be manufactured from wood or from plastic. Table 2 shows the data from a life cycle assessment and LCA for a wooden window frame and a plastic window frame. Both window frames are the same size. So they're going to ask us to compare and evaluate the use of wood and plastic. Let's have a little look. Of course they are. Evaluate the sustainability. So sustainability means the long-term use so that there's enough for future generations. We have to take that into account. So if I'm using wood, is there going to be enough for future generations? Is it going to be sustainable? If I'm using plastic window frames, is that going to be sustainable? So we're evaluating the sustainability. You should include environmental and economical factors. So almost, I want to say 3 marks on environment, 3 parts on economic is how I want to break that down. Now, so we want to break it down in terms of finances and in terms of the impact on the environment. Let's go back up to the table. I'm going to write my answer there. What you might want to do is pause the video, study the data, try and make 3 points for wood and plastic, both in taking into account the environment and the financials. And basically, you want to say good and bad about both. And then maybe I always like to finish my evaluation with a sum up saying which one I think is best. And it doesn't matter, there's no correct answer here, as long as you can back it with a piece of evidence, receipts from the data. All right, guys, I'm going to go through the answer. So hopefully you had a go with a pen and scrap paper. Well, let's go through. Sources of hydrocarbons used for production in kilograms. So this used 5.37. So first of all, I want to say wood is more sustainable as uses less hydrocarbons, um, which are non-renewable in its production. So I'm saying, look, there's less hydrocarbons, which are non-renewable, used in the production. So I'm showing you that I know that hydrocarbons are non-renewable, a little bit of peace there. Greenhouse gases released during production, use and disposal. So actually, they're pretty equal. They are almost equal on greenhouse gas released, which cause global warming. See how I'm linking greenhouse gases to global warming? I'm showing the examiner I know that greenhouse gases cause global warming, just like to show that off. They're almost equal. If we want, we could say wood is slightly less contributing factor to uh, climate change, like global warming, because of that, right? So that wood is going to, using wood and window frames has a smaller impact. Okay, oxides of nitrogen and sulfur dioxide produced in arbitrary units, right? Plastic produces plastic produces more air pollutants, such as sulfur dioxide, which causes acid rain, so does nitrogen dioxide, and nitrogen oxides, which cause respiratory things like asthma issues. So breathing problems, you could just say rather than using the word respiratory. Okay, I've run out of room here, so I'm going to continue down the side over here on the right. Now, so far it's all looking like wood is far better. Waste materials in kilograms. Again, it's looking like wood all the way through here, isn't it? Is better. So wood produces less waste materials. And let's be honest, the waste materials from wood are likely to be biodegradable. Um, it's probably not on the mark scheme, but and are probably biodegradable. So afterwards, wood rots down, plastic doesn't. So that makes it better. Let's also check it out. Total energy consumption in production, use and disposal in MJ is about So the energy production is similar. Whoa, energy production is similar. Um, and energy um, will cause fuels to be used. So um, environmental impact. Basically, if you're using energy, how does that link to the environment? Well, obviously, um, when you burn fuels to create energy, you impact the environment through global warming, greenhouse gases, that type of stuff. So I could go into that if I want, but I'm kind of running out of room. I'm going to allow that. Lifetime cost to the buyer. So the only really thing plastic's got going for it, to be honest, is that plastic is cheaper, and that is in the lifetime cost. So plastic has cheaper lifetime costs to buyer. And really, that is fairer on in people in poor countries. So this enables people who have less money to have more for food and other um, resources. So we might all say, yeah, it means that wood is the best, but at the end of the day, if you're saving £50 on your window, right, per kilo, remember this is per kilogram of window frames, your house will have, or your apartment or your flat will have a lot more than 1 kilo of window frames. So if you're saving that, that could be food for your children, that could be money for your children's education, that could be toys for your children's birthday party. So that isn't just a simple, oh, it's only £50 cheaper. That could be really important stuff. Okay, and that's really it. That's my evaluation. Now, what I recommend, I've run out of room, so I'm not going to put one, is that you put a conclusion, and all evaluations should come with your conclusion at the end. My conclusion would be that taking into account both of or the data as wood is more sustainable and less damaging to the environment, it is the better option in terms of sustainability and cost. It's only 50% more expensive and blah, blah, blah. Yeah, it's far better for the environment. There we go. That would be my overall conclusion. Right, let's move on. Right, let's move on. That was long. Right, five. This question's about the Earth's atmosphere and the Earth's resources. After the formation of the Earth's early atmosphere, the amounts of nitrogen and oxygen in the atmosphere changed. Explain the main changes in the amounts of nitrogen and oxygen in the Earth's atmosphere. Nitrogen increased, but nitrogen is still high in the Earth's atmosphere. So nitrogen increased as ammonia was released from volcanoes. So you've got nitrogen in the form of ammonia, which was released from volcanoes and from denitrifying bacteria. They're the bacteria in the soil of the earth that takes nitrates in the nitrogen cycle and returns them to the atmosphere in terms of nitrogen N2. Now, oxygen, what happened to oxygen? So you get a mark for decrease, and this is why I don't like this question. I mean, there wasn't really any oxygen in the Earth's early atmosphere. Volcanoes didn't release it in the Earth's early atmosphere. And the oxygen came a lot longer after the nitrogen. So the oxygen came due to photosynthesis from green plants, algae, that type of stuff. So let's put that down. So we want to say oxygen increased, 1 mark. So just for explaining the change, because of photosynthesis, everybody knows this fundamental process. Sorry, stupid song. Right, oxygen increased because of photosynthesis by green plants and algae. There we go. Bosh, 4 marks. 1, 2. So one for saying the gas increased, one for the explanation how. Okay. Describe how coal was formed from the carbon dioxide present in the Earth's early atmosphere. So, how was coal made? How describe how coal was formed from the carbon dioxide present in the Earth's early atmosphere. So, yeah, right. CO2 was absorbed into trees Now, you can probably just say plants, but CO2, and what's the process by which plants use sunlight and take in carbon dioxide and water to make glucose? So carbon dioxide was absorbed into trees by photosynthesis. You can probably say plants. So but really coal comes from trees. So carbon dioxide absorbed into trees by photosynthesis. And what's it turned into? If you remember the photosynthesis equation, I'm going to put this as well, whether it's on the mark scheme or not. It was turned into glucose, which is also turned into starch and stored in the trees as complex organic molecules like starch. Okay. Then what happened is, how did it get turned into coal? Some trees were turned into coal. We call this fossilization, not something you have to know exactly, but you do have to know by heat and pressure over millions of years. So the key things you might be thinking, where do all the marks come from? So I'm going to go through what is likely to be on the mark scheme because what is on your syllabus out of what I've written. Carbon dioxide was absorbed into trees by photosynthesis. So CO2 goes into the tree by photosynthesis. You're probably then going to get the other two marks for saying heat and pressure over millions of years. Those are the things that you had to know. So fossil fuels were made over millions of years by heat and pressure as the conditions. All right, let's go. The combustion of 1 kilogram of coal produces more carbon dioxide than the combustion of 1 kilogram of natural gas. Suggest why. So really, it's just a suggestion. Coal contains more carbon. So coal contains more atoms of carbon per kilogram. But we could also say coal is a solid, so has a higher density than a gas. The particles are closer together, right? In a solid. You know the solid diagram where you draw all the balls in lines, and a gas diagram where you have spaces between the balls. So coal is a solid, so it's more dense, so more carbon atoms per kilogram, right? Okay, let's zing on. Metals are extracted from metal ores found in the earth. Describe how bioleaching is used to extract copper from low-grade ores. So what's this all about? You might be like, I haven't heard of bioleaching. So bioleaching is where we have a rock. I don't know why my rock is brown, but that is our rock, our metal ore. And what we do with bioleaching, we take bacteria. Look at this incredible bacteria. There's its pili, there's its little whatever. And yeah, there's our bacteria. And the bacteria live on the rock and they extract the metal from the metal oxides in the rock and they form a liquid which they release. And then we can use a process called electrolysis or displacement to remove those metals from the liquid. So I need to put that down into writing. So I'm just going to say bacteria absorb um, metal ions from rock, or instead of rock, they've used the term low grade ore, so that's what I mean. They produce a solution containing the metal ions called a leachate. So they're going to make a liquid that contains like metal ions called like a leachate. So you got like copper 2 plus or whatever. Now, how are we going to get them out of that liquid? There's two methods that you have to know, and you can use this in phytomining or bioleaching. And these are the two methods to extract the metal ions from the resulting solution. And what you can do is use displacement with a scrap, more reactive metal, a scrap iron. Iron's more reactive than copper. So if you put some old iron in there, it's going to extract the copper out. Or use electrolysis. And so your three marks are for bacteria, create a leachate, use displacement, or electrolysis. Bosh. Let's go to the next question. Oh, it's giving me a headache. 5.5. Phytomining uses plants to extract nickel from low-grade ores. Plants contain 0.792% nickel by mass. The plants are burned to produce an ash. The ash from these plants contains 4.8% nickel by mass. Calculate the mass of ash produced from 1,000 kilograms of plants. Give your answer in grams in standard form. And it's worth 4 Badman marks. Oh, you're going to need your calculator. Oh, just have to bend down. That's the problem with being a fatty. Right. Okay. So what we want to do here, they're telling us that the plant contains, so let's do a lovely drawing. You can probably do this. It's actually not so hard. You just need to know how to times with percentages. So they're saying that the plants contain 0.792% nickel by mass. Calculate the mass of ash produced from 1,000 kilos. So first of all, how much nickel by mass is in these plants? Um, so what we want to do is how much nickel is in the plants. So I'm going to do 0.792. I basically need to divide that by 100 and times 1,000 to find out how many kilograms of nickel are in the plants. So 0.792 divided by 100. That's what you do when you times by a percentage. You divide by 100 and then times by, whoopsie, 1,000. So if I do that, I go 0.792. When you want to times something by a percentage, divide by 100 first, guys. And that is going to tell me that I have 7.92 kg of nickel in the plant. Okay, so we get our pile of ash because we set fire to our plant. So we burnt it away. And they're saying that of the ash, 4.8% of that is nickel. So calculate the mass of ash. Well, the ash is going to contain all of that nickel, which is 7.92 kilograms. So what I want to do is 4.92 over 4.8 and work out how many kilograms in a percent. So divided by 4.8 equals, so there's 1.65 kilos in 1%. So so that's in 1%. So how much in 100% of the ash? So in 1% of ash, there's 1.65. So I'm going to times 100. There is 165 kg in 100% in the ash. So that's going to get me another mark. But look what the answer said here. We had give your answer in grams in standard form. So that's a little bit of a bummer. Right, kilo means 1,000 grams. So I need to times by 1,000, and that is going to get us 165,000 grams. But it wants the answer in standard form. Of course it does. So standard form is when you do this. So we're going to convert it to 1.65. So 1.65, and then what we got how many numbers after the first number? So 5. So times 10 to the 5. So what I do to work out times 10 to the, I just count how many numbers after the first number. So after the decimal, I put my decimal there, there are 5 numbers after it, so I put 5 there. 1.65 times 10 to the 5, and that will get you the last mark. Oh, and that's grams, of course. G. Okay, that wasn't nice. I hate those kind of mental maths questions. Right, we're on. I think this is the last question. This question is about catalysts and equilibrium. What type of substance is a catalyst in a biological system? Algae, alkene, enzyme formulation. The answer is an enzyme. Speed up reactions without getting used up themselves. Explain how a catalyst increases the rate of reaction. Right, there are 2 ways. It basically lowers the activation energy, which is the minimum energy for bonds to break. It lowers the activation energy by providing an alternative pathway. And people often write things like, oh, it doesn't get used up and things like that. But basically, it lowers the activation energy, increasing the. I might just put for the hell of it. No, I'm not going to put increase. It doesn't increase collisions. It just makes more collisions are more likely to be successful because it's lowered the activation energy. Anywho, okay. I'm getting tired now. 6.3, the reversible reaction for the production of ammonia is N2 gas plus 3H2 gas goes to 2NH3 gas. What can scientists predict using Le Chatelier's principle? Okay, so using Le Chatelier's principle, they can predict the yield of ammonia or the position of equilibrium. So they could the shift in position of equilibrium when the conditions are changed. So they can predict the yield of ammonia or the shift in the position of equilibrium when the conditions are changed. That's a long ass answer. Describe how a reversible chemical reaction is able to reach equilibrium. So you have to be reversible to reach equilibrium, and you have to be in a closed system. So in a closed system, a reversible reaction will reach equilibrium where the forward and backward reaction rates are equal. So you have to be in a closed system where no reactant or product can be added. So that's what a closed system is, a beaker with a lid on, basically. That's going to get us our marks. Now let's sing on. Explain the effect of increasing pressure on the yield of ammonia, and it's worth 2 marks. We're going to need to take a little look here at this equation and zoom in. So bish bash. Oh my gosh, I think I went a bit too zoomy. Right. If you increase the pressure, what you need to do is count the gas molecules on either side of this reversible symbol. And so there are 2 gas molecules over here. How do I know? There are 2 of these. And just to show, because some of you might be like, I don't get why there's 2. Well, that is 1 ammonia, NH3, and that is counted as 1 particle. So pressure comes from the amount of collisions caused by the particles. So obviously this is the low pressure side to the equation, as there are only 2 gas molecules or 2 moles of gas on that side. Whereas over here we have nitrogen like that, and we just got 1 nitrogen, but we have on this side, we have 3 hydrogens, and each one of these is counted as a separate particle. And that means we have 4 gas particles over here. So this is the higher pressure side because there's more collisions, boom, 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 banging around over there than over here. So if we increase the pressure, Le Chatelier, this dude, he said that the reaction will do the opposite. So if you increase the pressure, it will go to the side, which will reduce the pressure, and that side is going to be to the right. So increasing the pressure will force the reaction to the right so that it tries to reduce the pressure by making less gas molecules, less collisions. Let's go put our answer in. Let's delete all of that. Oh my gosh. Here we are. Explain the effect of increasing pressure on the yield of ammonia. So we get 1 mark for saying, well, ammonia will increase. So the yield of ammonia will get bigger. We'll have more ammonia, and we'll say because the equilibrium will shift to the side with the least gas molecules. And this is because of Le Chatelier's principle to oppose the change in pressure. In order to lower the pressure, basically, to oppose the change, it will shift to the side with the least gas molecules. Bosh, right. Oh my days, come on. The forward reaction to produce ammonia is exothermic. So the forward reaction gives out heat. Explain the effect of increasing temperature on the yield of ammonia. Let's go back up, people. Brrr. So what they're telling us is that this is exothermic, and if the forward reaction is exothermic, then the backwards reaction is endothermic. We always name reactions. So the Haber process, which is this reaction, is an exothermic reaction. We always call them by their forward reaction. And what I like to think of is that the exothermic side to a reaction is hot and the endothermic side is cold, but never use hot and cold in your exam. You won't get any marks for it. So I like to think of that as the hot side and the cold side. So if we increase the temperature, which direction will it go? Le Chatelier, the dude down here, with his principle, he said that the reaction will do the opposite. It will always try and oppose, go against what you do. So if you increase the temperature, the reaction will shift to the endothermic cold side, and that is going to decrease the yield of ammonia because it's going to shift there to try and reduce the temperature. So that's how I like to work it out. Let's zing down here and put our answer in. So explain the effect of increasing temperature on the yield of ammonia. So ammonia yield will decrease. So you're going to get a mark straight away from saying that, as the equilibrium will, this is the language you've got to use, will shift to the endothermic side to oppose the increase in temperature. I think you could probably just say it will shift to the left. Rather than the endothermic side, or you could say backwards. There's lots of ways to refer to that direction. So it's going to shift towards the reactants to oppose the change. So you'll get less ammonia. And there you go. That's the end of the question. Don't forget sharing, caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Make sure you hit the like. It helps the algorithm. Make sure you join or become a member, whatever, subscribe. No, members different. Members $1.99 a month. You get access to my back catalogue of videos, which is just a load of extra videos. And you get first access when I release a walkthrough, because I always release them on the members channel for a week or 2 weeks or a month first before going out to public. So you can become a member, or you can just stay as a subscriber and you're going to get all the videos as well, other than the members only. All right, nice one, guys.
You're still here? It's over.